Hello CS11, this is lecture 19. In this lecture, we will be going over algorithms. So at the end of last lecture, we went over how brute force, although it's always correct, it's not always efficient. So in this lecture, we're going to see what efficiency is, and after that, we'll look at a few simple algorithms that will help us solve many different kinds of problems. Alright, so let's start first. To motivate efficiency, let's first have these two functions over here. So what are these two functions? The one on the left is a function for computing the Fibonacci numbers. And actually, the one on the right is also the same function. It computes the Fibonacci numbers. So if I put this, let's say I have a file fib1.py where I have this function over here. So let me just fix this. So we have this first fib function. Let's say for I in range 30 or for n in range 30, let's print fib of n. Then on the other hand, we have this other implementation here. So for this one, this is the cumulative version. So there's extra parameters here to keep track of the partial results. So if I now call the same thing, so here I called 0 to 29, I'll do the same thing for this function over here. Okay, so what should happen here is if I try to run fib1.py, it should give me the first several Fibonacci numbers. So let's try to print out more of these numbers. Let's say 50 and 50. Okay, so if we try to run each of these now, let's see what happens. So if I run this first one, you'll see that for the first few numbers, it's really fast, but as it keeps going on, it eventually gets slower and slower. So by this point over here, computing the next Fibonacci number is already a lot slower. On the other hand, if we try yung second implementation, we'll see that it gives us the 50 numbers instantly. So from the first one all of the way down to this last one over here. While yung first one only reached, I think it was around this point over here. So why did this happen? Why is there a difference between this first implementation and this second implementation? Okay, so as you can see here from what I just demonstrated, even if your code is shorter in terms of the actual lines themselves, that does not always mean that this is going to be faster than this. The important part is what actually happens inside the function. Okay, so let's go to another example to more easily see what kind of difference we're working with. So this is the index pairs function. We went over this during comprehensions. So this just generates all pairs I and j, where I is less than j. So we usually use this function if we want to get pairs out of some kind of sequence. And this is one way of implementing that function. Another way is using the subsequences function. This was what we had in the last lecture. So a pair of indices, this is just the same thing as a subsequence that has a length of 2. So what we can do is get all of the subsequences, then filter out the ones that have a length of 2. That's another way to get all of the index pairs like this. So the question is, are these two implementations the same? So should we be implementing index pairs like this? So if you think about what actually happens, so let's say I have this first one here. Let's put this in interactive mode. So here you have your first index pairs function, and if we do print then index pairs 20, we'll get all of these pairs over here. And if we have a subsequences function, we can also try to implement this. And the point is, if we keep doing inputs like these, so let's say 25, 30, 35, and so on, for this first implementation here, where we're just doing a nested comprehension, this is going to be fast. So as you can see, we're getting the answer instantly here. But for the other implementation, if you write subsequences again, then implement index pairs like this, what you will notice when you run each of these is that if you try to run it on larger and larger inputs, it's going to get slower and slower. So just like yung Fibonacci example, these two do the same thing, but they differ in terms of how long they take to run. So that's the main difference between these two implementations over here. Alright, so why does this happen in the first place? Okay, the main idea for why these two implementations take different amounts of time is, well, what's actually happening inside these lines over here. For the second one, it's getting all subsequences first. And we know that if you have a sequence of length n, the number of subsequences is 2 raised to n plus 1. So if n was 3, for example, there are 2 raised to 3 plus 1 subsequences. On the other hand, if you use this implementation instead, this is just a nested for loop or comprehension. So for this the first implementation, there are only n times n plus 1 over 2 pairs in this range over here. So the idea is these are meant to reflect the number of operations you are doing in these functions over here. The 2 raised to n plus 1 is for this one, and n times n plus 1 over 2 is for this one. So if we try to substitute these inputs, 20, 25, and so on, to each of those functions here, what we're going to see is that, let's say we have a function that returns 2 raised to n plus 1, and you have a second function that returns n times n plus 1 all over 2. So if I have f of 20, then g of 20, you'll see that f of 20 is already a lot larger than 210 here. And if we keep doing that for larger inputs, the difference gets bigger and bigger. So let's say 30. As you can see, when we reach 30, this is already a lot larger than the n times n plus 1 over 2 here. So the point is, this 2 raised to n plus 1, this grows a lot faster than n times n plus 1 over 2. And because of that, for larger inputs, you're doing this many operations for the first implementation, while you're only doing this many operations, or this many operations for the second implementation, and this many operations for the first implementation. So they're very different numbers, which explains why one of them, or the first implementation, is a lot faster than yung second implementation. Okay, so note that when it comes to comparing how fast two different functions, for example the ones here, when you want to compare how fast these two functions take, we usually compare them using large inputs. Since for small inputs, again, we mentioned that our computer is very fast. So for small inputs, regardless of what our function actually does, let's say f of 5 and g of 5, if our inputs were just 5, then the difference is kind of negligible. It's for larger inputs where we really start to see the difference between how many operations each of the functions actually does. So yeah, that's why we only usually care about large n. And in general, what we really care about is how fast these functions grow. Or in other words, how or what their growth rates are. Okay, so there's one main way to compare the growth rate of two different functions. For example, yung 2 raised to n plus 1 here, and yung n times n plus 1 over 2. If we have two of these functions, we say that one of them grows a lot faster than the other one if we take the limit and yung f over g, if this is equal to infinity, for example, if f was yung 2 raised to n plus 1, and if yung g was this function over here, the limit of this over this is equal to infinity. You should be able to derive that from math 21. So since the limit of this over this is infinity, we usually say that yung first function, this grows a lot faster than this second function here. We have a notation for that. We say that yung g of n, this is small o of f of n. So in other words, what we're saying here is that n times n plus 1 over 2 is equal to small o of 2 raised to n plus 1. Or this function grows a lot faster than this function over here. Okay, so note that when it comes to making our computers do things quickly, what we want is functions that grow slowly, not quickly, since as you can see from a while ago, if we have a function that grows insanely quickly, then our computer is eventually not going to be able to handle this many operations. So yeah, what we want is functions that grow slower. Okay, so all of this efficiency stuff, we're not going to analyze that formally here in CS11. Usually where you do that, at least for those in CS, we usually do that in CS32 or 33 instead, yung data structures and algorithms courses. So for CS11, what we're basically going to do is what we did here. What we're going to do in CS11 is just estimating using functions that we know and plugging in yung input sizes to those functions. So we're not going to be very precise about how we define yung efficiency. What we're going to do at a high level is figure out functions that represent how fast or how quickly these functions grow in terms of their input, then substitute different input sizes to those functions. Okay, so for our example, just by comparing 2 raised to, for example, if the sequence had a length of 1000, if we try to compare this 2 raised to 1000 and this already tells us why one function is a lot slower than the other. 2 raised to 1000 is, 2 raised to 1000 is whatever this big number is, while 1000 times 1000 plus 1 over 2, it's just 500,000. So this number is definitely larger than this number, which is why the function here, which only runs approximately this many operations, is a lot faster than yung function which takes around this many operations. Okay, so for our cases, what we will usually do is we're going to assume that for each second, our computer can run around 100 million operations. So for example, if we run 500,000 operations, we're going to assume that our computer can do that at a rate of 100 million operations per second. So this is a lot smaller than 100 million, so it's going to take a very short amount of time. On the other hand, for this guy over here, if you divide this by 100 million, actually we can do that. Divide this by 10 raised to 8, it's still some ridiculously large number. So imagine this number in terms of seconds. If we try to get this number of minutes here, that would be around this, and the number of hours is then, oops, and this is the number of minutes. If we try to get the number of hours, we divide by 60 again. So this amount of hours, let's divide that by days. So 24 hours in a day. So this many days, if we divide it by 365, so running the first, or running the slow implementation, the one that uses all subsequences, and giving it an input of 1000 is going to take this number of days. So we probably don't want to wait that long. So yeah, that's why we usually prefer yung faster functions over yung slower functions like these, since it's very unrealistic to actually make our function run for this long unless you're very patient. So yeah, this is our estimate that we are going to use. Okay, so when it comes to operations, for example, checking if something is in some container or clearing something, all of these are not what we call primitive operations. When you say primitive operations, what you usually mean is just addition, subtraction, the usual arithmetic stuff, as well as other operators. Then there are some functions that we can consider primitive. For example, for a list, appending and popping, we will consider these primitive. But for other operations like these, that might not be the case. Since depending on what structure you're actually using, they could be slow. For example, this x and y, this is slow if y is a list. We went over this before. And x.clear is always going to be slow since you have to get rid of all of the elements in this container here. Okay, so the point of yung algorithms courses 32 and 33 is to be able to come up with faster functions like these. So if I go all the way back here, the point of the algorithms and data structures courses is to figure out faster, more efficient solutions to many different kinds of problems. So here in CS11, what we're going to do is just lay the groundwork for that. We're going to go over some of the most basic ideas behind common algorithms and how we can use those to solve relatively simpler problems. So you can think of this as a preview for 32 and 33. Alright, so let's go over some different problems where there are many different kinds of solutions with different efficiencies. Alright, so let's start with this over here. So we have a sequence and we want to find the sums of all subarrays with a length of k. So for example, if I have 1, 2, 3, 4, 5, 6, let's say I have, let me use a file instead. So if I have the list 1, 2, 3, 4, 5, 6, and I want to find all subarrays of length 3, then those would be 1, 2, 3. Then if I adjust this, this would be 2, 3, 4. Then this is 3, 4, 5, 4, 5. Then finally, we have 4, 5, and 6. 4, 5, 6. So these are the subarrays, and you want to find the sum of each of these. So this has a sum of 6, this has a sum of 9, this has a sum of 12, and this has a sum of 15. So you have these these subarrays, and these are their corresponding sums. So given this array, how do we get all of these sums over here? So this is one example. 3 plus 1 plus 4 is 8, and so on. Alright, so the first solution, as we mentioned in the previous lecture, if you have a problem like this, the first thing you should think of is brute force. So what is a solution that will definitely work? Well, we want all of the subarrays that have a length of k, so let's just go over all of those. So here, it's iterating over the starting index of the subarray. Then here it gets the sum of that subarray. So this will be a correct solution. Let's try to run this. So if I have this and I try to print out subarray sums, then 1, 2, 3, 4, 5, 6, where k is equal to 3. Oops, this should be here. And if I try to run this, Python 3 algo.py, this should give me, let me get all of the elements there. This should give me those subarray sums that I want. So this is a solution that would work. Okay, so the problem with this is that it's actually going to be slow for large inputs. Let's show that here. So if instead of 1, 2, 3, 4, 5, 6, I give it something like list, then range, let's give it 10 raised to 4, or 10,000. So this is the numbers 0 to 9999, and I want all subarray sums of length 3. So if I run that, you'll see that it takes a bit since it has to print out all of the stuff here. If I make that input even larger, let's say 10 raised to 6, then as you'll see, it's going to take a bit before it actually outputs all of these. So the point is, this is going to get slower and slower for large inputs. Alright, so why is this solution slow? Okay, if we think about what's happening over here, the number of subarrays we're considering, let's go back here. For this example, there is n is equal to 6, that's the number of elements, and if k is equal to 3, the number of subarrays that we consider is going to be 1, 2, 3, 4. And another way to look at this is, if you want the number of starting indices, you start from index 0 all the way until starting from index 4, or index 1 until index 4 here. So another way to write that is going to be n minus k plus 1. So there are this many subarrays, and you multiply that by the number of elements in each subarray, since you're getting the sum of that specific subarray. So this multiplied by k. So all in all, you're doing around this many operations. So this is what we want to consider. Okay, so this is the number of steps, and if k is around half of the length of the sequence, then this is going to become n squared over 4. So just to demonstrate that here, if this was n minus n over 2 plus 1 times n over 2, then this is roughly equal to n over 2 plus 1, n over 2, or this is around n over 2 squared, or n squared over 4. So in that case, if n is 1 million, then 1 million squared over 4 is around 250 billion. And this divided by 100 million is a big number. So this is going to be slow for inputs as large as this. So 2,500 seconds, 40 minutes. So this is a lot slower than what we want. What we usually want is our function to only take around a few seconds at worst. If it takes 40 minutes, that's already pretty bad. Okay, so can we do better? Can we find a faster solution to this problem over here? So as it turns out, we can. And for that, the idea we have to use is that if we have two subarrays beside each other, they have very related sums. What do I mean by that? So here, you have this subarray, which has a sum of 6, and yung next subarray has a sum of 9. If you notice here, these two subarrays, they do share the middle elements in common. So this 1, 2, 3 and this 2, 3, 4, both of them have yung 2, 3 in the middle. If k was 4 instead, so this is 1, 2, 3, 4, then this is 2, 3, 4, 5, both this subarray and this subarray have this component over here, 2, 3, 4. So what that means is, formally, if you have some subsequence, this is your sequence, and you have some subarray over here. So this is your subarray. So Si is the sum starting at index I. So if you have S of I plus 1, or the next subarray after Si, this will be equal to this. From the definition, it's just this element plus so on until k elements after. So if you try to get the difference of these two, they will share all of the elements for Si, all of the elements after Xi, for S of I plus 1, all of the elements before X of I plus k. So what you'll end up with here is the difference between these two is just equal to this element minus this element. And because of that, if you add S of I to both sides, you'll have S of I plus 1 is equal to Si plus this. So what that means is, to get the next subarray sum, you only need to perform a single addition and a single subtraction. So that will now give us this solution over here. So what's happening here is that you have your initial subarray sum, or from the first k elements. Let's get this over here. So this is your initial subarray sum. Then for the next subarray sums, what you're going to do is add the next element, then remove yung front element. So for this example, let me use k is equal to 3 again. So for this example, what's basically happening is, you can think of it as some window that's moving one step at a time. So at the first step, it covers these 3 elements. Then in the next step, this moves one step forward. So it now covers these next 3 elements. And the next step is the next 3 elements, then so on. What we're just representing here is what changes after each step. And that's the new element as well as yung front element here. So if we have this, and we now try to run this function here, this is going to be a lot faster. If we don't print that, or let's run this, there, something like this. So if this was 10 raised to 7 and I ran that, you'll see that this here, this takes a few seconds. Let's actually time that. I'll go .pi. If we try to run this, this is going to take us around 3-ish seconds. But if we used yung old solution over here, the one that takes around n squared time, where n is the length of the sequence, this one would take a lot longer. So this is around 5-ish seconds. So this here, another thing we can do is, this is just 3, so if this is a small number, then this is just approximately going to be equal to n. So if we make this around n over 2, so 10 raised to 7 over 2, if we do that for the first one, it's now going to take quite a long time. So as you can see, quite a lot of seconds have passed already. So let's stop that. If we try yung second one instead, if we try the second one, so this second one over here, if we try to run that, this will only take 2 seconds, even for this same input. So the first one hasn't stopped after 12 seconds. The second one already finishes after 2 seconds. So as you can see, this is now a lot more efficient. Okay, so because the number of steps here in each iteration is only constant, or it's just a single addition and a single subtraction, the total number of operations that we go through here is approximately equal to how long the original sequence is. So from this example, we can see that depending on the problem, it's very important to find the right algorithm. Not just a solution that works, but also a solution that runs fast enough. So in the last lecture, we said that don't be clever, but for some problems, and in fact for a lot of problems in computer science, you do have to be clever in some way. But of course, it's always nice to have some fallback, some solution that you know would work, so that you have something to start with, which is why we went over brute force in the previous lecture. Okay, so let's look at a few more algorithms. Before that, a note on the next few labs and the last, or hope 3. So being able to come up with these clever ideas that I mentioned here, that will take a lot of practice. So please do the practice sets. If you come across a algorithm or a solution that wasn't familiar to you, try to dig deeper into those algorithms. Some of the points will definitely depend on them, and in fact, for some heartbreak points, they already did. So yeah, again, if you want to try to solve problems like this, always start with brute force. Then, since you want fast solutions, it's important to be able to know how to measure if your program is fast or not. So it's also important to be able to estimate how long your program runs, which is what we've been doing throughout this lecture. Okay, so aside from that, usually for each problem, there are constraints. Constraints. So how big will the input get for that specific problem? So the constraints will also tell you if your solution is fast enough or slow enough. So if, for example, if you see something like n is at most 350,000, and you have a solution that takes around n squared steps, if we get 350,000 squared, this is a big number. If we divide this by 10 raised to 8, it's this many seconds, which is a lot larger than the limit that's set in OJ. So if you have a problem where this is the max input, then a solution that takes around this many steps is not going to pass. So that will tell you that you might have to come up with a faster solution. Okay, so now let's look at a different problem, or a slightly related one actually. So this time we have n numbers, and we also have q pairs of integers here. So for each of those pairs, you want to find out what the sum of the subarray from this index to this index is. So for example, if you have this array or list, and you have these pairs over here, for 0 to 3, that's index 0 plus index 1 plus index 2. So 3 is exclusive, so 3 plus 1 plus 4 is equal to 8, which is why this corresponds to the 8 over here. For the second one, 1 to 5, that's 1 plus 4 plus 1 plus 5, and that is equal to 11. So you have to figure out how to get these subarray sums from these inputs over here. Okay, so one very quick way to do that is, let's have sub range sums. You have a sequence and you have some pairs. So what you can do here is, for I and j in pairs, since you want the subarray sum from I until before j, what you do here is just yield the sum of sequence from I until j. And that's literally it. So if I try to get this now, this will give me the output that I want here. So as you can see, just literally doing what the problem asks you to will already give you a correct solution. But the question now here is this a fast enough solution? So this is the brute force one. But as it turns out, this is going to be slow if your sequence is big and you have a lot of pairs to check. So let's see what's happening here. For each pair, we're getting the sum of however long that pair is. So for example, if the pair asks you to get the sum of the entire list, then that would be around n operations for that particular pair. And if there were q pairs, so n times q. So depending on how large n and q are, if n and q are around 100,000, then n times q is going to be 10 raised to 10. So 10 raised to 10 divided by 10 raised to 8, this is 100 seconds. So that's pretty slow. So this is how you make that explicitly. So if you try to make a large case like this, you will see that your input or your function here is going to be slow. So how do we work around that? So let's try doing this one step at a time. What if we only consider the pairs where I is equal to 0? In other words, we only consider yung prefixes, or we only consider the problem for prefixes. In that case, what we can do is we can pre-compute. So before answering the questions here, let's first try to compute all of the prefix sums of this array here. So this is all of the prefix sums, and from the prefix sums, we already know that if our pair asks us to get the sum from I until j, where I is equal to 0, this will correspond to one of the elements in this prefix sum. So we just yield the corresponding element. So this will now correctly answer the pairs where I is equal to 0. So in this case, it's only this first pair over here. But now, this solution is, well, fast, at least for answering these pairs over here. Because this process now, for each pair, there are at most q pairs. What we're only doing here is an if-else. And in that if-else, we're only yielding or raising an error. So we do a constant number of operations for each iteration. And because of that, what we have here is q pairs multiplied by around a constant number. We usually use 1 for that. So this is around q operations. So if q was 10 raised to 6, this is 100,000 operations, and 100,000 is a lot smaller than 100 million. So in that case, this would be fine. This would be a fast enough solution. But of course, this does not cover, or this does not yet cover, this case over here. What if I is not equal to 0? Okay, so here we have the q part is from here, and there's also an additional n here for building the prefix sums. So this is actually n plus q. N plus q times 1, or n plus q times 1, which is n plus q. So if n and q are both 100,000, this is still a reasonably small number of operations. Alright, so how do we now handle the case if I is greater than 0? So if I is greater than 0, we can actually use a important insight over here. And that is, if we want any subarray, let's say 5, 6, 7. So let's say here, if we want this subarray, 1, 5, 9, that's just the sum of everything until 9, the sum of all of this, minus the sum of the first few elements before 1. So if I want to get the sum of 1, 5, and 9, what I can do is I get the sum of all of this minus the sum of this prefix here. So essentially, for any subarray, it's just a difference of two different prefixes. And we already know what the prefixes are since we computed yung prefix sum array over here. So what that means is that since here the way to answer each pair is now a single subtraction, so that's now a constant number of operations. So what that means is to set up yung prefix sums, that's n, then for each pair it only takes us a constant number of operations to answer that question. So this will give us the same n plus q function for the efficiency of this new implementation over here, if we use this idea. So depending on how you actually implement all of this, for example in prefix sums here, yung actual indices that you will have to use might be a bit different. So be careful for which index you actually use in this final formula over here. Okay, so for example, for here, the way to answer each pair is just a single difference. So this will now give us all of the answers that we want for each pair over here. And to answer each pair, we only do a single operation here. So this is now fast. It answers the question correctly, and it is also fast. Okay, so this function has a runtime that's proportional to n plus q. And yung earlier example natin, yung brute force one, over here, the number of operations for this one is proportional to n times q. But what are these proportional to things over here? So when we say that yung runtime is proportional to n plus q or n times q, what we're really saying is as n and q grow, yung runtime of our function, of our algorithm, is approximately equal to these functions over here. In CS, we have additional notation for that. So we had small o a while ago. If we want this proportional to relation, we use what we call big O notation. So that's big O of n plus q, or big O of n times q. So this is the notation that we use to describe the efficiency of these functions over here. So for the formal definition, you will likely see this in CS32. But for now, you can think of big O notation as this function runs approximately as quickly as this function here, or this solution takes around this many steps. So that's what big O notation is. So for our case in CS11, what we'll usually say is some function, some algorithm, has a worst case running time of around whatever function it's similar to. So here, for this solution, for the subarray sums, Our solution has a running time that's big O of n plus q. So this is usually how we describe efficiency in computer science. Okay, so if you want to know, if you want to know the formal definition, feel free to ask us.